My name is Sven-Erik Gryning, and I will tell you about wind resource assessment. Wind resource assessment basically means how much energy can you extract from the wind by use of a wind turbine. So the objective is that you should be able to have an idea about the main principle of wind resource assessment, what is important, what is not important. You should be able to know the three main components of the wind atlas methodology, and you should be able to reflect over the different types of terrain, how that will affect the wind speed and how that will affect the energy you can extract from the wind. So here we have a description of the classical problem. You have a carbon anemometer to the right in the picture. You want to measure, you want to put up a wind turbine, or you have a wind turbine, but you also have a very complicated terrain. You can see you have to the left you have a water, a beach, you have an escarpment, and then you want to put up the wind turbine somewhere. So the question is, how do you do this? You want to use the measurements you can see from the mast to the right. You have very good long-term measurements, but how do they represent the wind where the wind turbine is? So the worst thing you can do in such a case is that you can make a linear interpolation. In this case, we have a carbon anemometer here. We know the wind here. We know the wind here. So therefore, we know the wind here and here. However, the terrain is complicated. For example, you have a forest here, and you can see that when you have a forest, the wind speed decreases because of the forest, the high roughness of the forest. You have a hill here, and over a hill, the wind speed increases, at least very close to the hill. So here you have a much higher wind speed than you have over the forest, and maybe the distance is only a few kilometers. The carbon anemometer here is actually placed where there is a house, so there is a sheltering effect. There's an object here. So therefore, the wind speed is actually a little lower than it would be if you had a free terrain. So in a way, this illustrates very nicely how sensitive the wind is to variation in the landscape types. So in the wind atlas methodology, we use this idea that we base the estimates on real measurements, but we have developed a way such that we can change, so we can transfer the measurements from the meteorological site to a site where you, for example, want to put a wind turbine. And the idea follows what I have just told here, that we take into account the effect of obstacles. In this case, I mentioned that the meteorological measurements were near a house. Then we compensate for this in the meteorological measurements. Then we compensate for the specific roughness, and then we compensate for the topography in the area. In this way, we make a generalized wind climate. That means that we take the measurements from a real site, and then we clean them in such a way that they represent a flat terrain with a specified roughness that we can actually specify. Then we have something we can use. We can go the other way, and we can go down. So if we want to predict the wind climate here, you can see that the wind climate at a specific place for a wind turbine, we first take into account the topography, then we put into the model the roughness of the terrain, and then if there are any obstacles. And in this way, we have made a model that can be used at a specific place that is within the same overall wind climate as the meteorological mast. So this is an example of the way we take into account the sheltering effect in this model. It's a fairly simple, it's a parameterized way, but you can also see here that the sheltering effect can be very big, up to 50%, very close to a building, and even 30 obstacles height, you can still see the effect of the obstacle there. So this is built into the model, and this is the way we compensate for the effect of obstacles, being buildings or groups of trees. So another point is that you have changes of roughness. And these changes of roughness means that you can go, for example, go from the wind goes from the sea over the land. When it goes from over the sea to the land, it changes the turbulence, and it also changes the wind speed. And here we have an example where it's illustrated. We have the wind profile over the sea, which is almost vertical. And then we have a roughness change here. And here we have a higher roughness, in this case 20 centimeters. The green area here shows the area where the wind speed is in equilibrium with the new surface, and also the turbulence is in equilibrium with the new surface. The height of this area, it increases with roughly 1 to 100. Then we have another area up here where actually the wind profile is in transition. That means that it partly reflects the over water conditions and partly reflects the surface condition. So in this case we can use an interpolation between the two, and above an internal boundary layer, actually the wind profile is exactly the same as over the water, or almost exactly the same as over the water. It's very characteristic for this that here in the green area, the turbulence is equilibrium with the surface here. If you go up here, we have an area where the turbulence is not in equilibrium, but the wind profile is in equilibrium with the oversea conditions and the interpolation layer here. So this was how we treat the roughness changes. The third part of the model is that we also treat the inhomogeneous terrain in terms of topography. And what is characteristic is that when the wind blows from a flat terrain and meets a hill, the streamlines are compressed on the top because of continuity, and therefore the wind will speed up at the top of the hill here. Here we have an idealized example, and here you can see how it actually works. You have the wind profile over land, the flat terrain, and you have plotted the same wind profile here, but over the hill you have an overspeeding. The overspeeding can be quite large, but it's also on the height of the L here of the maximum overspeeding is connected to the length or the width of the hill. So therefore it's a very good idea if you want to put up wind turbines to put them on top of the hills. But small hills are not good for large wind turbine. There has to be a certain connection between the size of the wind turbine and the dimensions of the hill. But put up a wind turbine on a hill can give a much higher energy production than if you just put it over land. Here we have an example of a time series of real observations from Denmark. And you can see that the wind speed at 10 meter is here. It's of course lower than the wind speed at 100 meter, which is a fairly typical hub height today. Maybe the hub height is even higher for some of the new wind turbines. And it has a very characteristic daily variation here. This represents one specific day. You can see that during the night, the wind speed between 10 meter and 100 meter, the difference is quite big. And this has to do with stability. It's pretty sure that during this night it has been a cloud-free night, so you have a strong cooling of the surface, which inhibit the momentum transfer, and therefore the wind speed is much lower at 10 meters than at 100 meters. During the day, when there are a few clouds, you have a very pronounced mixing of the whole layer, and therefore the difference between 10 meter and 100 meters decreases. And then it's characteristic that when we come to the night here, we can see that the difference is not so big, which can be an indication that actually we likely have clouds developed here, so we have a near neutral wind profile. So when we do the calculations, we do not really use the individual measurements because this will be quite time consuming for the computer. It is possible, of course, but they are put into a Weibull distribution, and this is a typical example of the Weibull distribution. You can see it is a quite nice fit to the measurements, but it's not a perfect measurement. And the Weibull distribution is just chosen for practical reasons because it's very easy to do calculations on the Weibull distribution. So when you have done all these calculations, when you have taken care of the obstacles, the roughness, and the topography, you can come up with an assessment of the wind energy. And here we see an example of the assessment. You can see it's wind turbines put on a ridge, and the red indicates the energy content in the wind that can be produced by the wind turbines. And it's clear that it's a good idea to put on the ridge here, and there's less energy in the wind when you just move a little away from this. So what did we learn here? We learned that the wind resource depends on the surface roughness, it depends on the orography, and it depends on the sheltering by obstacles as a first approximation. And in the program we use, the WASP, all this information is represented in digital maps of the wind farm and the neighboring area. The maps has to be quite big, so it's quite a large job, but it's to produce them, but it's a very important job to produce these maps.